So here we are in 8.2, and here's where we'll start getting some trigonometric definitions that are here. So let's just consider the complex number 2 plus 3i. In 2 plus 3i, we can relate 2 plus 3i to what they're going to say is a vector, right? So this is all related to the vector stuff that we did at the end of 7. But to view it like that is a little bit over the top. When you graph 2 plus 3i, what you want to recognize is that the x-axis is the real axis and the y-axis is the imaginary axis. So we can plot complex numbers in what they call the complex plane. So the complex plane is a place where we can plot complex numbers and work with them, see them being added and other things. So where is 2 plus 3i? It is literally the real part is over 2 and then up 3. And that is where it would terminate. This is the complex, this dot right here is the complex number 2 plus 3i, right? But they'll often represent it as a vector. So again, what did we do? We went over 2 and up 3. If we grab something like negative 2 plus 9i, we would go over negative 2 up 9. 9's right here. And draw this large vector right here. Okay, that's negative 2 plus 9i. And so that's how we graph things in the complex plane, is we plot their real part and their imaginary part. Now you can start to see where some angle stuff is going to come in, right? We can start defining things there we go. We can start defining things based upon a magnitude and a vector right there, and we do that because it makes them work really, really nice. And so I think that's enough to get the idea. If you had something like 6 minus 7i, we would go over 6 and down 7, which would bring us to right here. And we would, let me draw that one in blue so it just stands out. I'm trying to pick them in different quadrants. But we would draw the line that's like just like that. Okay? And be able to identify that complex number in the plane. So write a few complex numbers and add them. I don't think I need to do a few, but let's look at something like this. 4 plus I plus 1 plus 3i. Now you know how those add. So this is, in some respects, I feel like this is a kind of silly in order to do this graphical interpretation, but it does work. So if we looked at 1 plus 3i, where is that? Let me just plot that out. So I'm going to graph the 1 plus 3i. Here's 1 and 3 i's. It's going to be just like this, 1 plus 3i. And then in red, I'll graph the 4 plus I. So 4 plus I would be over 4 and up 1 in the I direction. Now, I'm not really good at this, but I'm going to come here in yellow. See how if that stands out. And if I draw my parallelogram, they behave just like vectors. And the resultant vector is the addition of the two. Well, what should that resultant vector be? Now notice it's a little bit pushed out from here. It's probably more up like this. But it appears to be at the 5 level. Well, that's exactly what I'm going to get. 5. And then what level? Yeah, 5 plus 4i. So I didn't draw mine up as steep. It should be coming in right into this area right here. Right? If I were to draw my parallelogram a little bit better, mapping that out more, it would have gone up like that and been the 5 plus 4i. But you knew it was going to be 5 plus 4i. The algebra is better than the graphs, and we've known that for a long time. The graphs, though, is necessary in order for us to get a relationship. So the rectangular form of a complex number, before we said a plus bi, we want to now call it x plus yi. That way it corresponds to an x and y. direction. Now remember, x was the real number part, and the real axis was the x-axis. Y is the imaginary number. So they're choosing this for a reason. So if we have the complex number x plus yi, it looks like this. It's that directed vector, right? That directed line segment, which we call a vector. That vector has a magnitude, which I'll call r, and a direction, which I'll call theta. And we know a lot. Take a look at this relationship. I'm just going to draw a red line down. You know that this distance across here is x and this distance across here is y. So what do we know? We know that x is equal to r cosine theta. Now how do we know that? We know cosine theta is adjacent over hypotenuse. But if you knew the magnitude and the direction, you could get your x. You know from a similar nature that sine of theta is equal to y over r, or y is equal to r sine theta. You know that r is equal to the square root of x squared plus y squared, always positive. R is always a magnitude, which is positive. And the tangent of theta is equal to y over x. Of course it is. Tangent was always sine over cosine. Sine was always the y. Cosine was always the x. And so these relationships we know quite well from before. And it really helps us to get to solve some problems when we can get what they call the complex form or the polar form of a complex number. So let's get what the polar form of a complex number is. So they use this word polar. Polar is often trigonometric in nature, so I would call it a trigonometric form as well. Let's start with the rectangular form. The rectangular form was x plus yi. And what we now know is that because of how x plus yi looks, x is, if I needed it, a polar form is one that has an angle, right? A magnitude and an angle. And so we know what x is. X corresponds to cosine. So this is r cosine theta. The plus sign is the plus sign that was there. The y is r sine theta. And the I was always there. That is the polar form. Now we simplify that a little bit by saying it's r cosine theta plus, and they move the I in front, I sine theta. So that's the polar form of a complex number. You can see that right below. The polar or trigonometric form of a complex number is z is equal to r cosine theta plus I sine theta, where r is the magnitude of the vector, in this case, because we want to consider it to be a vector, and but r we know is the x squared plus y squared, right? But remember that's what magnitude was. Like if we go back to chapter 7, it was just the a squared plus b squared underneath, and the angle is the angle that's created between the x-axis and the vector. And so we often choose theta between 0 and 360. We don't have to. And then here's an abbreviation that they'll use in the book. RCIS theta. I shouldn't have said equal. So R the magnitude times cosine I sine of theta. So they want us to find the sum of these complex numbers and graph their resultant. So I think the worst thing that you could do is do the parallelogram. I think you should just sum them up. 2 minus 4 is negative 2. 3i and 2i is 5i, and graph the resultant. Negative 2, 1, 2, 3, 4, 5, and do your best to just get that in the right area. Negative 1/5, and so, yeah, they're going to pick fractions because they love you. I got to take a negative 1/5 and add to that 3/7. So what's that look like? That's negative 7/35 plus 15/35. 15 minus 7 is 8/35. So I got 8/35 plus, and here I got 2/7 minus 3/4. So what's that? That's 8 over 28 minus 21 over 28. And 21 minus 8 is 19 over 28. Am I thinking about that right? No, I'm not thinking about that right. I don't know what I'm thinking. Okay, so if I look at 21 minus 8, okay, 13, sorry, 13 over 28, losing my train of thought here. So we get a 13 over 28, and it's negative, right? So let me make that a minus I. And then you just do your best to plot those fractions. 8/35, closest multiple, the 8 times 4 is 32, so it's about a quarter, right? So I'm not sure why they would want you to plot that. It's a little bit lame. Wouldn't see something like that on the exam, but it's just like the last section, we're adding up some things that just happen to be fractions. So write each complex number in its rectangular form. It's pretty easy. Remember what this is. This is, in order to translate from polar form to rectangular form, all you have to do is do the trig. And remember what this is. So what is the cosine of 135 degrees? Hopefully you know that it's negative root 2 over 2 almost instantaneously. It's in the second quadrant, has a 45-degree reference angle, so it's going to be a root 2 over 2, and all students take calculus. So the cosine will be negative, but the sine will be positive. Now we're not done yet. We need to distribute through. And when we distribute the 6 through, we get negative 3 root 2 plus 3 root 2I. And we're finished. That's the rectangular form of that. How about this one, negative 60 degrees? So let's think about where negative 60 degrees is. We know it's in the fourth quadrant with a 60-degree reference angle. So we have to ask ourselves, hey, in the fourth quadrant, cosine's positive. What's the cosine of 60 degrees? I believe it's 1/2, positive. Sine's going to be negative, though. And if it's 1/2 there, it's root 3 over 2. And now we need to multiply through by root 2. So I get root 2 over 2 minus root 6 over 2I. And that's its rectangular form. So as we go to this next one where we write each complex number in polar form, remember there's just two things we need to find. We need to find r and theta. Well, r is easy. R is equal to the square root of x squared plus y squared. We saw that in the beginning. So r is equal to the square root of 1 squared plus root 3 squared. R is equal to the square root of 1 plus 3. R is equal to the square root of 4. R is 2. So now we know r is 2. Now how are we going to get theta? You're going to use the fact that tan theta is y over x. Now, in order to get the right thing, we need to know what quadrant we're in. So it would be wrong for me to just go answer this question. Where is this vector at? 1 plus root 3I. It's in the first quadrant, over 1 and up root 3. So this is a first quadrant angle. So when does tangent theta equal root 3? Hopefully you remember that that's a 60-degree angle. And they want it in degrees as noted above. And so what do we have? We have that this complex number has a polar form of 2 cis 60 degrees, or 2 cosine 60 degrees plus I sine 60 degrees, however you want to write it. Either way is fine with me, in the condensed form or the expanded form. But it's only 60 degrees because it was a first quadrant angle. Take a look at what would have happened. I think it's wise to look at this. I'm going to come in here in red. I'm going to change this number. Come in here in red and change this number. I want us to look at negative 1 minus I root 3. Nothing would change here. This would have been a negative 1 and a negative 3, but it would have still yielded an r value of 2. This would have been a negative root 3 over negative 1, which would still have been a root 3. But this 60 degrees is no longer good. Because where is negative 1 minus I root 3? Negative 1 minus I root 3 is down here. 1 to the left and root 3 down. Therefore, it's not 60 degrees, but it's a 60 degree reference angle in the third quadrant, so it's 240 degrees. And we would have had 2 CIS 240 under that new heading. I think you'll see that in the future ones as well. And some should be really easy if we have understanding. So maybe the first thing I should suggest is, number one, graph out what you have. Where is negative 2 plus root 2i? It's in the second quadrant, over 2, up 2. Awesome. Let's go find out what r is. R is equal to the square root of negative 2 squared plus 2 squared. Well, what's that? R is equal to the square root of 4 plus 4. So r is equal to root 8. R is simply 2 root 2. Nice. What's tan theta equal to? Well, it's equal to y over x, which is negative 1. Well, we know the thetas that make that happen. They're 45 degrees. So I need a 45 degree angle in quadrant 2. Well, that 45 degree angle in quadrant 2 is 135 degrees. And so the answer is r, 2 root 2, CIS, 135 degrees. You put 45 degrees, it's wrong. Right? Not right at all. Negative 45 degrees, wrong. That's not where that thing is. Negative 45 degrees is not even allowable because you need your answer to be within 0 to 360, but it still wouldn't have made any sense. How about negative 2i? If you follow my advice, this one's almost done. Where is negative 2i? It has nothing in the real direction, and it's coming down here too in the imaginary direction. Well, tell me, how long is that line? Well, it's 2. That's pretty obvious. It's straight down from 0. What's the distance between 0 and the endpoint? 2. Harder here when it was going off at an angle. Couldn't just name it. But here it's 2. What's the angle that it's at? Remember, it wants it from 0 to 360? Easy. 270 degrees. And so we're done. The polar form is 2 times the cosine of 270 degrees plus I sine of 270 degrees. And we don't sweat that. Okay. Describe the graphs of all complex numbers z satisfying the specified condition. The absolute value of z is 1. So when they say the absolute value, they mean the magnitude. So what's the magnitude? The magnitude is the distance between 0 and any point. So you're picking points that are all 1 away from the center. You're going to get a circle of radius 1. That's all the complex numbers that have that are out a distance of 1 will form a circle of radius 1. It wouldn't matter what angle you're at. You're just out 1. The real and imaginary parts are equal. So if you have real and imaginary parts that are equal, your lines look like this. Your points look like this. And so what do they look like? They look like the line y equals x. I hope that's not too fast, but if you're real and imaginary, so think about that. That's 1, 1, 2, 2, 3, 3, 4, 4, negative 1, 1. And so when I say 1, 1, 1 plus I, that's 1, 1. 2 plus 2i, that's 2, 2. Negative 2 minus 2i, that's where your real and imaginary parts are equal. They would all line up. The real part of z is 1, and your imaginary part can be anything. So that is, well, let's see. It looks something like that. 1 plus bi, or 1 plus yi, if we use that other notation. So what's 1 plus bi look like as b is allowed to change? Our 1's locked into place, but our imaginary part can go any way that it wants. Oh, we get the line x equals 1. And so the reason they're doing this is they want the equations to make sense when they bring them up. The imaginary part is 1. That means I can have any number as the real part, but my imaginary part's locked in at I. So I could have any real, but my imaginary is always 1 up. Well, that's the line y equals 1. Okay, y equals 1 would be that guy right there, because your imaginary part's locked in there. Your a can be anything. Awesome. So that's it for 8.2. Just that brief introduction to the polar form or the complex form of, I'm sorry, the polar form or the trigonometric form of complex numbers.